Welcome to section 4.4, day 3, applications of sinusoidal functions. Today's objectives are to model data using sinusoidal functions. Modeling data using a sinusoidal function. We have a table here and it says the tides in the Bay of Fundy in New Brunswick, Canada have extreme highs and lows every day. The table shows the high tides for one lunar month. Write a trigonometric function that models the height of the tides as a function of time x, where x equals 1 represents the first day of the month. So we have this table. What we would do is we'd plug this in to our calculators, which we put in our table, and list 1 and list 2. We would do a scatter plot, and what you get is the picture on the bottom right. This is our scatter plot, and it looks like a sine or cosine function. This looks like it'd be a sine or a cosine function. We have to figure out which one we want to use. We're going to write an equation from this. The way this one is peaking, I would probably use a cosine function, and then we will do a shift. Our cosine function has a peak right here, and we can use this because on the y-axis, our cosine, our parent function, is at 1 when we have 0 degrees. So we can use this to help write an equation. To write the equation, we are going to look at our max and min values and determine our A, B, C, and D for our function. And when you look at the table that was on the previous page, the max is at 28 on day 17, and the min is 23.3 on day 10. We can use this to find our amplitude, because the amplitude is half the distance between the extremes. If we take 28 and minus 23.3, and we take half of that, half the distance gives us the amplitude. When you do this, you get 4.7. We're going to divide that by 2, and we get that our A is 2.35. That is my amplitude, 2.35. All right, so you'll notice that this thing is not on the x-axis, it is up, so we have to do a vertical shift. D is our vertical shift. And what we do is we want to find out where the midline is, basically. We find out what the average of the extremes is. So now we're going to add the max and the min together and divide by 2, and that will give us our midline, which is our shift. When you do this, you get 51.3. We're going to divide that by 2, and when we do this, we get 25.65. That is my D, halfway between the max and the min. Now we're going to look at how often this thing repeats. So if we look at our max and our min is down here, our max is up here, and our max happened at day 17, our min happened at day 10. So to go from the lowest to the highest, it took 7 days. That is half of the period. So we want to double this. So we're going to take 2 times 7 days and get 14 days. This is the period. It repeats every 14 days. It's going to go up and down every 14 days. So to find the B, our B is 2 pi, because that's the normal function for cosine, over 14. And when we solve this, we get pi sevenths is our B. And hopefully you recall that P, the period, is 2 pi over B. We're trying to find the B. We plopped it out. We know our 14 is our P for our period. So we get B is pi sevenths. Now we have to look at a phase shift. You notice usually the cosine function is at 1 when the angle or the x is at 0. Well, now our max value is happening on day 17. So we are shifting this 17 units to the right. So our phase shift, if you remember from our handout, is negative the opposite of C over the absolute value of B. Well, we know that we're shifting 17 units. So we know we have 17. It equals the opposite of C, which we're trying to discover, over our B, which is pi sevenths. If we want to move the pi sevenths to the other side, we multiply both sides by pi sevenths. I'm also going to do a negative at the same time so we get a positive C value. So we multiply both sides by negative pi sevenths. This wipes out the denominator, it changes this to positive, and we get C is negative 17 pi over 7. That is my C. Now that we have our A, our B, our C, and our D, we can write our function. See if I can squeeze it in here. So our function, y equals my A, which is 2.35. I chose use cosine, so cosine. My B is pi sevenths. That's multiplied by x. My C is negative, so I'll need to have a negative sign there. Negative 17 pi over 7. And my shift was plus the 25.65. And I'm running out of room, but it's 25.65 there in the bottom corner. Okay, that is my function. 2.35 cosine pi 7th x minus 17 pi over 7, and then add 25.65 at the end. And if we graph this equation over our scatter plot, it would match up decent. It wouldn't be perfect, but it would model what's going on. All right, so that's how we build an equation just from the graph here. We find our A by doing amplitude is half the distance between the extremes. Our vertical shift is the average of the extremes. Then we look at how long it takes to go from the lowest point to the highest point. Double that. That is our period. We can use the period to find the B. And then we look at, if like this one we're doing a cosine function, how would we shift to get it to where that would be at 0, where that high point is at 0. And this one we have to shift 17 units. Okay? Here we have modeled data using a sinusoidal function again. The table here shows the average monthly high temperatures for Chicago. Write a function that models the high temperature using x equals 1 to represent January. So you'd put this again in your calculator to do a scatter plot. It does say to use this as 1. That means December is 12. We're going to plot these in, do a scatter plot. And this is what we get. And then this will repeat again the next year. This is just what's happening every January through December. And in January it starts back over, so it repeats itself over and over and over every year. We're going to do the same thing we did on the last slide. We're going to find our A, our B, our C, and our D. And again, we're going to find our max and min values to determine A, B, C, and D. Our max is 84 in July. Our min was 32 in January. That was from our table. Again, the amplitude is half the distance between the extremes. So we take our max, subtract off our min, divide it by 2. We get 84 minus 32 over 2. This is 52 over 2, which is 26. So 26 is my A. The vertical shift is the average of the extremes. So we add the extremes together, and we divide by 2. This is 116 over 2, which is 58. The period is the time it takes to repeat, or twice the time to go from max to min. Well, this is a cyclical for the year. This is going to repeat every 12 months. So our period is 12. And if you looked at this, we are actually repeating every, from low to high is 6 months. And if we double that, we'd also get 12. So our P is 12. We want our B, and our B is 2 pi over the period. This is pi sixths. And we'll leave it in pi sixths. We will not turn it to a decimal. And then we're going to look at the phase shift for our C. We're going to use cosine again because it's easy to shift this peak to the y-axis. That's why it's easier to use. You could do the sine, but it's a little harder to figure out where the midline is and do some other stuff for the shifting. This one's pretty easy to do since our peak can be easily shifted. All right, so cosine usually reaches its first max at 0. Our graph hits its max in July. We are shifting 7 units. That's how far we shifted. So again, we know our phase shift is 7. And we know our period, our B I should say, we know our B is pi over 6. And again, like we did in the last one, we have to multiply by negative pi 6 to make our C positive and to remove our denominator. When we do this, we find that C equals negative 7 pi over 6. That's my C. So we have a C, we have a B, we have a D, we have an A. Now I just got to find a place to write it. See if I can squeeze this in. All right. So our equation is y equals RA, 26. We're doing cosine. Our B is pi 6 times x. Our phase shift is negative 7 pi over 6. And our D is 58. This is the function in cosine that represents this data. All right, if we would have chose sine to use, we would have a different equation, but it could still be used to represent the data. For these ones, a lot of these are easier to do a shift with the cosine function. Let's move on to our last part for the day. All right, here it says, write a sinusoidal function with the given period and amplitude that goes through the given point. Our period is 3 pi. Our amplitude is 0.5, and we want to go through the point pi square root of 3 over 4. All right, so a couple of things we know. We have period is 3 pi. We can go and figure out right away what our B is. So our B, if you recall, is our normal period over our new period. So this is 2/3. Our B is going to be 2/3. This 0.5 is our amplitude, so that's my A, 0.5. All right, we can use these to help us figure out what's going on for this point. When we have the amplitude of 0.5, that means we're going to multiply the y by 0.5. So whatever we normally get from our y coordinate, we multiply by half, or 0.5. So if you think about this, this is the same as 1/2 of y. So what would have to be y if 1/2 of y is the square root of 3 over 4? Well, that means the y has to be the square root of 3 over 2. So we are looking for where we get y coordinates of square root of 3 over 2. Well, there's only a couple places we get square root of 3 over 2 as our y coordinate around the unit circle. It can happen 2 different places, in the first and second quadrants. This can happen at pi thirds or 2 pi thirds. Those are the 2 places it can happen at. So now we look at this B. So these are the 2 places it can happen. Here is my B. My B is 2/3. When we set up our equation, we're going to have one of our sine or cosines. Actually, since we're doing the y, we'll do the sine. That's where we have the y there. And our B is 2/3 x. We don't know, actually, I'm going to write this in as 0.5 already. We don't know if we have a phase shift. We aren't going to worry about that actually on this one. And a D. This is what our normally looks like. So we have to multiply whatever our x is by 2/3. So we look at this. If we have our pi here and we plugged it in and we had 2/3 pi in there, well, 2 pi over 3 is right here, and that gives us that square root of 3 over 2, which is what we need for this point. So without having to do any shifting or anything like that, we just have our equation is, I'm going to rewrite this as 1/2 sine of 2/3 x. This is my function. With this period, this amplitude, and this point, if we plugged it into this equation, we would have that point with what we have our A and our B as. We didn't do any shifting. When you guys do these today, there's only a couple you have to do like this. The idea is you think about how you get to that point from a coordinate pair on the unit circle. We are not doing any horizontal or vertical phase shifts. It's just going to be an equation that looks similar to this. It could be a cosine function instead of a sine function, but the idea is the same. We are not going to shift them. Okay? A lot of what we did here is just showing you how this works. Once you found the 2/3 and the 1/2, since we aren't doing any shifting vertically or horizontally, it's just going to be this function. You just got to figure if you want the sine or cosine. This one's a sine because we're looking for All right, that is all for section 4.4 day 3. Today we're looking at applications of sinusoidal functions and how to write equations off of a scatter plot, or if we're given a period, an amplitude, and a point. Thank you for watching, and have a nice day.